Hello everyone, myself Vinay Kumaram. I am pursuing PhD in physics. So in this particular YouTube channel, I will be teaching physics, chemistry and mathematics starting from 8th standard till 12th standard. So if you want to learn physics, chemistry and mathematics starting from 8th standard till 12th standard, then you have to subscribe to my channel. Please do subscribe to my channel. So in my previous video, I was explaining the exercise questions of 11th chapter of 9th standard science subject. That was on sound. So there I have explained 5 questions. So in this particular video, I'll be explaining the next questions which are there in this particular exercise. So now moving on to the 6th question in this particular exercise. So in 6th question, they are asking to calculate the wavelength range of sound waves which human ears can hear. So human ears can hear the sound in the frequency range of 20 Hertz to 20 kilohertz. So that means you have to calculate wavelength range for this particular frequency range, and you should consider the speed of sound as 344 meter per second. So here they have given speed of sound and they have also given the range of hearing of human ears, that is 20 Hertz to 20 kilohertz frequency. So now you have to calculate the wavelength. We know that velocity is equal to lambda into nu. So lambda is wavelength and nu is frequency. Now you know what is the velocity, you know what is the frequency, you have to calculate lambda. So that means nu you can take to LHS. So when you take nu to LHS, so it will become V divided by nu, which is equal to lambda. So lambda is equal to the first nu you can take 20 Hertz. So lambda is equal to velocity is 344 meter per second. So it is in SI unit. So I can directly substitute 344 divided by 20 Hertz is there. That is also there in SI unit. So directly you can write 20. So here 2 tens are 20, 2 17s are 34, 2 twos are 4. So 172 divided by 10. So that is nothing but 17.2 meter is the minimum wavelength of sound when it is traveling at 344 meter per second in order human ears to hear this particular sound. So now you have got answer as 17.2 meter. So this is one wavelength. You have to calculate other wavelength also, that is at 20 kilohertz frequency. So always remember lambda is equal to V divided by nu. So nu is in the denominator. That means if frequency becomes more, then wavelength reduces. So that means now the wavelength should be lesser than 17.2 meter. So velocity is 344 meter per second divided by nu. Now we are taking 20 kilohertz. Kilo means it is 10 power 3. So 20 into 10 power 3. So the same thing will be there here also, that is 17.2. But this 10 power 3 is also there. So that 10 power 3 will be there in the denominator. So when you, because I am doing 34 divided by 20. So 34 divided by 20 is 17.2 and 10 power 3 is there. So 10 power 3 will be there in denominator. When it comes to numerator, it becomes 10 power minus 3. 17.2 into 10 power minus 3 meter. Or you can bring this decimal point to the left hand side. So that will be 0.0172 meter. So that means the range of this wavelength is 0.0172 meter to lambda is equal to 17.2 meter. So here frequency is 20 kilohertz. So here frequency is 20 kilohertz and here frequency is 20 hertz. So we have calculated wavelength for both the frequency, that is in between 0.0172 meter to 17.2 meter. So this is the wavelength range for the frequency starting from 20 Hertz to 20 kilohertz. Coming to the 7th question, here there are 2 children of your age and these children are holding aluminium rod in their hands like this. So one kid is holding this aluminium rod from one side and the other kid is holding this aluminium rod from the other side like this. Now the first kid hits this particular aluminium rod with some object and this particular second kid hears the sound generated when this kid hits this particular aluminium rod like this. So when he hits, this particular sound travels through the aluminium rod as well, and this sound will also travel through air as well. So now you have to calculate the ratio between time taken. So now you have to calculate ratio between time taken for this sound wave to travel both in aluminium rod and in air. So now in order to calculate time, what is required? The distance is required, the distance traveled by the sound wave and the velocity. So because V is equal to d by t, so if you bring t to LHS and V to RHS, V will go to denominator and t will come to the LHS. So t is equal to d by V. So this is the formula which we have for time taken by the sound wave to reach that particular distance. Now here we will take t1 as the time taken. So t1 is the time taken by sound. So t1 is time taken by sound in air. So let's say time taken by sound in air is as t1, and let us consider t2 as the time taken by sound in aluminium. So T2 is the time taken by sound in aluminium rod. So this is T2, and the time taken by sound, the same sound wave in air, is T1. Now you have to find ratio between T1 and T2. So T1 is equal to d by V1. So V1 is the velocity in air. So velocity of sound in air, and T2 is equal to d by V2. So this velocity is the velocity of sound wave in aluminium rod. So remember this, and in both the cases d remains constant because the friend is standing just next to the aluminium rod. So that's why distance in air and distance in aluminium rod is more or less same. So that's why d is constant. Now you have to find ratio between the time taken in air and the time taken in aluminium rod for that particular sound wave. So that is, in order to take ratio of time taken, here you can take T1 by T2. So what is T1? T1 is d by V1 divided by d by V2. So now this d and this d gets cancelled with each other. So 1 by V1 will be remaining in the numerator, 1 by V2 will be remaining in the denominator. So 1 by V2, when it goes to the numerator, it becomes V2. So that means 1 by V1 into V2. So that is nothing but V2 divided by V1. So I am bringing this 1 by V2 to numerator. So when it brought to numerator, so that particular 1 by V2 becomes V2. So reciprocal of that you are taking. So 1 by V2, when it goes to numerator, it becomes V2. So 1 by V1 is there in the numerator. So 1 by V1 into V2. So that is nothing but V2 by V1. Now, in order to calculate the ratio, you require the velocity of sound in aluminium and in air. So this is the velocity of sound wave in aluminium, V2, and V1 is the velocity of sound in air. So if you refer your textbook, here there is a table where they have given the velocity of sound wave in different solids and also in air. So in aluminium, sound wave travels at the speed 6420 meter per second, and in air sound travels at speed 346 meter per second. So here meter per second gets cancelled because here we are taking ratio, there will be no SI unit. So 6420 divided by 346. So when you calculate this, you will get 18.555 as the ratio. So approximately you can consider this as 19. So T1 by T2, that is ratio between the time taken by sound wave in aluminium and in air. If you are taking, then that is equal to 19. So that means here sound wave travels faster in aluminium than in the air. So that's why time taken in aluminium is less and time taken in air is more. So that means here T1 is greater than T2. That is, time taken in air is more than the time taken in aluminum, because speed in the aluminum is more compared to the speed in the air. So that's why here when you take T1 by T2 you are getting 19. So 19 is the ratio between time taken by the sound wave in air to the same time taken by the same sound wave in aluminum. Coming to the 8th question, here they have given frequency of a particular sound wave. So frequency of a particular sound wave is equal to 100 Hertz. So 100 Hertz is nothing but 100 times vibration in 1 second. So this you can write as per second as well. So that means here 100 times vibration is happening. So 100 times vibration. So whenever you have this hertz, no? So if frequency is equal to 100 hertz means it is vibrating 100 times in 1 second. So that means here you have to calculate how many times this particular vibration is there in 1 minute. So that means in 1 second the number of vibration is 100. So what will be the vibration in 1 minute? So that you have to calculate here. So now if you cross multiply this, so this is equal to 1 second into x is equal to 100 into 1 minute. So in the place of 1 minute, I can write this as 60 seconds because 1 minute contains 60 seconds. So 1 second into x is equal to 100 into 60 seconds. So now you got 1 second into x is equal to 100 into 60 seconds. So this 1 second if you bring to RHS it will go to denominator. So x is equal to 100 into 60 seconds divided by 1 second. So this second gets cancelled with each other. So 100 times into 60. So 6000 times. So 6000 times vibration of this sound wave is happening in 1 minute. Coming to the 9th question, here they are asking, does sound follow the same reflection laws as light follows? Yes, of course. So answer is yes for this 9th question, and you have to explain how it happens. So I have already explained in my previous video. Briefly I will explain in this particular question as well. So whenever if you keep a particular normal like this to the surface, and on this surface if you are bouncing a particular light wave, when it hits this surface it reflects with the certain angle with this normal. So angle of incidence will be there and angle of reflection will be there. So this angle of incidence is equal to angle of reflection according to first law, and this incident ray, reflected ray and the normal lie in the same plane. So this is two laws which this particular light obeys, and the same law sound waves also obey. So here if you have a surface like this, and if at a certain angle a sound is striking this surface, and if you are drawing normal here, then along with this normal the sound wave will create another angle on the other side of normal, and that angle of reflection is equal to angle of incidence. Same as light obeys the laws of reflection, the same laws of reflection is applicable for the sound as well. So the incident sound wave, reflected sound wave and the normal lie on the same plane, and the angle of incidence of this sound wave and the angle of reflection of the sound wave are equal with each other. So these are the two laws which is applicable for sound waves as well. So that you can explain in your own words. For more detail you can refer my previous video where I have explained the laws of reflection of sound waves. So coming to the 10th question, here there is a source of sound and there is a reflecting surface. So here there is a source of sound and there is a reflecting surface. So the distance between this particular source of sound and the reflecting surface is exactly in such a way that this particular source of sound, or if a particular person is standing near the source of sound, can hear the echo. So that means they have exactly kept this reflecting surface where this sound wave can travel 0.1 seconds, can take more than 0.1 second in order to reach back the source of sound, so that person who is standing near the source of sound can hear this particular echo. Now here, if this same setup is done on a hotter day, so for example on another day, if this same setup is done, and on that day the temperature is little bit higher, that is there is an hotter day, so that means on a hotter day temperature will be higher. So on hotter day temperature is higher. So you all know that when temperature is more, sound travels much more faster, because speed of sound depends on the temperature. So if temperature is more, speed of the sound wave is also more. So now on a particular day, this particular setup was adjusted where source of sound and reflecting surface are kept in that particular distance, exactly at that particular distance where the echo can be heard. That's it. So more or less, if you bring the reflecting source a little bit near, you will not hear the echo. At this particular distance only that echo is heard. So that minimum distance where echo can be heard, at that minimum distance this particular reflecting surface is kept, and hence the echo was heard on this particular day. So if you consider this as day 1, on this day 1 echo is exactly heard. So echo is heard because it is kept at minimum distance where echo can be heard. Now on a hotter day, so let's say this hotter day as day 2, here source and reflecting surfaces are kept at same distance. So that's why from the source, when the sound travels to the reflecting surface and when it comes back, the distance what it is covering in day 1, that distance was a minimum distance to hear that particular echo. But on the day 2, when it was a hotter day, the sound wave traveled much faster. So on day 2 the temperature was higher. Because the temperature was higher, the sound traveled much more faster, and because the reflecting surface was kept at minimum distance on day 1, so on day 2 sound has traveled faster, so that means the same amount of distance it has covered in less time. So that means on day 2 it is not possible to hear echo, because on day 1 echo was heard because exactly the reflecting surface was kept at minimum distance in order to hear the echo. But on day 2, because temperature was increased due to an hotter day, so that time sound took less time to reach back the source again, because it has traveled faster than day 1. Sound wave has traveled faster than day 1. Because it took less time compared to the day 1, echo was not listened. But again on a hotter day, if the reflecting surface is moved a little bit far away from the source, then again echo can be heard. But here this reflecting surface is adjusted in such a way that echo is heard on day 1, but on a hotter day echo is not heard properly. Coming to the 11th question, here they have asked to give examples or practical applications where reflection of sound waves can be used. So in my previous video I have explained how stethoscope works, and also I have explained how megaphone works. So you can go and refer that particular video in order to understand how stethoscope work and how megaphones work. So in both these cases reflection of sound is used. The application of reflection of sound is used. And also reflection of sound is happening inside a conference hall and also in cinema hall. So in this hall also reflection of sound is happening in such a way that audience can clearly hear the audio of that particular movie, or in a conference hall if a person is speaking, then the whatever that person is speaking, if audience should hear it properly, then this particular reflecting surfaces are aligned, or the curved surfaces of the room is aligned in such a way that the audience who are sitting in that conference hall or in the cinema hall can hear the sound better. So this particular case is also an example for reflection of sound, and stethoscope, megaphones are also an example for reflection of sound. So this is all there in this particular video. The remaining questions which are there in this particular exercise I will be teaching in my next video. Till then, if you want to learn more physics, chemistry and mathematics starting from 8th standard till 12th standard, then you have to subscribe to my channel. Please do subscribe to my channel and stay tuned with my channel. Thank you.